Good afternoon, calculus class. So this one is section 2.7. So it's a regular calculus by James Stewart. And this one, so it's the derivative and the rate of change. So we call that the average rate of change. So this one is just like finding the slope, like y2 minus y1 over x2 minus x1. But in the calculus approach, so we put in f of x2 minus f of x1 over x2 minus x1, so that's the slope. Instantaneous rate of change is kind of like the slope formula, but we want to find out the slope at that specific point. As you can see that the graph right here, so once we find the slope at A, so started with that, the average rate of change from A to A1, A to A2, A to A3. So this one is getting close and close and close to that, the purple line right here, the instantaneous rate of change. So one thing that we notice, if the average rate of change is the same as the instantaneous rate of change, so that means those two lines, they must be considered parallel to each other. So two parallel lines, so that means the slope got to be exactly the same. So the way to find out the instantaneous rate of change, we need to take the limit. As you can see that x is getting very close and very close to the value of a. So the tangent line to the curve y equals f of x at a point a comma f of a, it's the line through point P with slope m equals the limit as x approaches a of the expressions f of x minus f of a over x minus a, and pro y the limit exists. So anytime that you see something like this, that means we're looking for the instantaneous rate of change. So definition, the derivative of a function at point A denoted by f prime of A. So if you see that the apostrophe like that, that means prime. It's f prime of A, so that equals the limit f of A plus h minus f of A. So again, A is just that the exact value, the exact x position. H, that's just the difference of x2 and x1 with the limit exists. Alternate form, you can always put it this way, f prime of a, so f prime of a equals the limit f of x minus f of a over x minus a as x approaches a, with the limit exists. So normally, I do suggest students to apply the alternate form, because that it's going to be much easier, so by the time you try to simplify it, so for the limit, it's not just considered the instantaneous rate of change, but that implies for the calculus now, so this one is called the derivative, the first derivative. So now let's find the equation of a tangent line to the curve at a given point. So first thing you want to do, you want to find the slope. And for those who might be wondering, can I use the derivative formula, such as like a power rule? Well, that's something we'll talk about in the next chapter. But so far, you have to stick with the limit definition of the derivative. So again, we're using that limit as x approaches a of f of x minus f of a over x minus a. So what we found here, so limit x goes to a, so a is what, negative 1. So f of x, which is the function itself, so 2x to the power of 3 minus 5x minus f of a, so minus 3. And then it's all over x minus a. So x minus negative 1, so x minus negative 1 or x plus 1. And now from here, before we plug in the limit, so this one you don't want to put in negative 1 because that will be undefined. So what we can do, we can simplify it a little bit. So 2x to the power of 3 minus 5x minus 3, it's non-factorable. But one thing that we can do, if you guys do remember back to Algebra 2, we can always perform the synthetic division. So the numerator, it's always considered the dividend. So we do have 2, x squared is missing, so it's 0. Minus 5, we take out those coefficients. And then negative 3. Divisor, which is what? The opposite of 1, so then that'll be negative 1. Again, first number, you don't do anything about it, bring it down. So 2 times negative 1, negative 2. Combine them, negative 2. So negative 2 times negative 1, then that'll be 2. Plus negative 5, then that'll be negative 3. So negative 3 times negative 1, positive 3. So this one can be simplified into 2x squared minus 2x minus 3. You guys see that? What happens if I don't remember the way to do with the synthetic division? You can use the long division. But that one, it's a little bit tedious, a little bit more work. So there's no more restriction remains. So what we can do, plug in the number. So it's 2 times -1 quantity square minus 2 times -1 minus 3. So this one is just -1 quantity square. It's 1 times 2. So 2 plus 2 and then minus 3. So the limit, the slope here, it's 1. So the slope at that point here, it's 1. And then find an equation. So you guys do remember that with the point slope form? The way to write the equation of a line. So it's y minus 3. So that equals m, which is what? The slope that we just found. And then x minus -1, so x plus 1. So this one is just like x1, y1. And then solve for y. So we do have y equals 1x. 1 times 1, that's 1 plus 3, then that'd be plus 4. Just like that. And now what about for part B? So part B, let me just put it into the next slide. With a brand new slide here. You know what, let me just open it up. Okay, so new slide with that square root of x. With the position of 4, 2. So once you plug in that 4 here, so y is what, 2. So the way to find out the slope at that position, again, we take the limit as x approaches 4, f of x, which is what, square root of x. There's no need to rewrite it in general form, so this one, just plug in that root x. Minus f of a, which is what, 2. Again, this one's a, this one is f of a. Divided by x minus 4. So one thing that you might be wondering, what can we do from here? Well, definitely you can either rationalize it, or you can just do something like reducing. But you have to factor something out here real quick. So let's just multiply by the conjugate of the numerator. Again, you cannot just plug in 4 because that would be undefined. So multiply top and the bottom by root x plus 2. So what we found here, it's x minus 4. Now denominator, you don't want to distribute, you don't want to FOIL, just leave it as the way it is. We just want to keep that with the factor form. And the purpose of doing this, guess what? We can reduce. So now what we found here, we got limit, x goes to 4. So it's 1 over square root of x plus 2. No more restrictions, so that means we can plug in the number. So x equals 4, so 4 square root of 4 plus 2. So it's 1 over 2 plus 2, which is what? 4. 1/4. But this one is just the slope. The slope at the point. The instantaneous rate of change. So this one's supposed to be m. And now using the point slope form. So using the point slope form, we can find out the equation of a tangent line. Again, the given value here, we do have x1, y1, so basically plug in the number. So y minus 2 equals the slope, 1/4 times x minus x1 minus 4. So what we found here, it's y minus 2 equals 1/4x minus 1. So that means y equals 1/4x. And -1 plus 2, which is what? 1. And that's the equation of a tangent line. Okay, so now going back to the rest of this. And example 2, this one has been done already. A particle starts by moving to the left along a horizontal line. When it's the particle moving to the right, moving to the left, standing still. If the particle is moving to the right, so moving to the right, so that means the velocity is considered positive, or the rate of change is considered positive. So if that's positive, that means the slope of the line segment must be positive. So as you can see that from 4 to 6, so you can tell that the slope is what? Positive. Rise over run. So from 4 to 6, the particle is moving to the right. And then from 0 to 1, so the particle is moving to the left because the slope is what? Negative. And then the particle still stands still, so that means that the particle is considered constant. So like from 1 to 4 right here. And then from 6 to 8, so that means the particle is still standing there. It's not moving. And then sketching the graph, so we do know that from 0 to 1, so the rate of change here is considered -3. So it's going to be like a staircase functions for this. And then from 1 to 4, so the particle is standing still, so that means there's no rate of change, so that's 0. And then from 4 to 6, the rate of change, what is that? It's rise up 2. Run is also 2, so it's 2 over 2, which is what? 1. So I should put in that scale here. And then from 6 to 8, so the particle is also standing still. And for those you might be wondering, the open circle, so the open circle, that's just like the end point, but it's not included. As you can see that the right, the left, the bound right here, those positions, the right end point, they're not included. Well, because that would be considered the initial time for the new rate of change. Okay, so now let's see what else that we have for the rest of this. Again, this one is already done. So find an equation of the tangent line to the graph of y equals g of x at x equals 4 if g of 4 is negative 2 and g prime of 4 is 3. Again, what this one tells you, this one is just a slope. And then x value, so that's the x1 value. And then g of 4, y1. So basically we're just using the point slope form. And then plug in those numbers and then simplified it, we do have the equation of a tangent line. And then example 4 might be a little bit difficult. So this one tells you the slope in a certain position. So for h of 0, that's 0 right down here on the bottom, at the 0, 0, the origin. And one thing that we notice, h prime of 0, it's nothing. So that means this one is considered a horizontal tangent. Horizontal tangent, so that means the slope is considered 0. And then for h prime of negative 1, it's negative 1. So negative 1, so that means it's declining. So negative 1, that shows the slope here. Rise over run. And then h prime of 1 is 3. So at 1, so the slope is a little bit deeper. It's positive 3. So it's right here, positive 3. Rise over run is 3 over 1. And this one here is negative 1 over 1. And then things that we have, so h prime of 2. So at 2, so the slope is 1. So the slope here, it's 1. So this one is less deeper. So once you're being able to connect those slope field, so this one's kind of like a slope field. So once you're being able to connect those, the little line segments, so then that'll be the curve. So it's a decreasing curve, increasing, and then decreasing. Well, actually the rest of this, it doesn't matter. It doesn't tell you anything right after 2 here. So we got 1, 2, and negative 1. Okay, so now what about finding f prime of a? Again, the way to set it up, so basically just find a limit. So the limit as x goes to a, so we do have f of x minus f of a over x minus a. So let me just move this one to the new slide. For example 5, I think this one is the last slide here. So we do have 2x plus 1 over x plus 3. So f of x, so that equals 2x plus 1 over 2x minus 3. But let me just double check this one here. 2.7. So 2x minus 1, no, over x plus 3. Excuse me. Over x plus 3. Okay, so 2x plus 1 over x plus 3. So the way to find out the derivative in general, we take the limit as x approaches a. So f of x minus f of a over the quantity of x minus a. So what we found here, so the limit x goes to a. So f of x, which is what, 2x plus 1 over x plus 3. Minus f of a, so 2a plus 1 over a plus 3. And then this one is all over x minus a. So this one would be kind of complicated. There's so many rational expressions. So what we can do, we can always convert this one together, multiply by the missing element, so we can convert that to the same common denominator. So multiply this one by a plus 3. This one here multiplied by x plus 3. x plus 3. So what we got here, denominator, it's what, a plus 3 times x plus 3. Just keep it that way. And now what about for those numerator? Well, from here, we can definitely want to FOIL. So a times 2x, so then that'll be 2xa. A times 1, then that'll be a. And then 3 times 2x, 6x. 3 times 1, then that's 3. And then minus the whole quantity of this one, 2xa. Again, FOIL, first outside, inside, last. So 2xa, and then 2a times 3, 6a. And then 1 times x, 1x. 1 times 3, that's 3. And then you might be wondering, what about that x minus a? So definitely we would need to put it in. Another thing that we can do for that x minus a, we can always put it this way. We can always multiply the reciprocals of the denominator. So it's 1 over x minus a. So let's cancel out the common element, 2xa, 2xa. Let's see things that we can cancel here. The 3 minus 3, so that's gone. And now we're left with a plus 6x minus 6a plus x. Okay, so right here what we can do, looks like we can combine those like terms. Okay, so let's try to combine those like terms and see what happens. So a minus 6a, so we do have negative 5a. Right here, a, 6a, but it's minus. So 6x minus x, we do have what? 5x. Okay, so definitely this one can swap those terms. So again, one thing at a time. Denominator, just leave that with that a plus 3, x plus 3. Again, we're taking the limit as x approaches a. So one thing that we found, so this one, once we swap those terms, so we can take out that 5. And also we can cross cancel. So take out 5, so we do have what? X minus a. Denominator, just a plus 3, x plus 3. X minus a, cross cancel. So what we found here, we got 5 over a plus 3. And then x plus 3. Remember, the value of x, what is it? It's a. So we got a plus 3, so eventually it's going to be 5 times a plus 3, quantity squared. Again, there's no more x. Everything's in terms of a. So now, this one will be the what? The derivative of this function here, in terms of a. So now, let's see what else that we have, going back there. So the other one, we do have 1 over square root of t plus 2. So it's a similar problem. But this one is even more difficult because that involved with the radical. So again, I'm going to put it into the new slide here. So 1 over square root of t plus 2. Okay, so the way that you want to set it up, limit as t goes to a. So we do have 1 over root t plus 2 minus 1 over root a plus 2. And it's all over t minus a. Again, combine them, so we just want to put in that root a plus 2 minus root t plus 2. All over the least common denominator, which is all those radicals together. Again, divided by t minus a, that means you multiply it by its reciprocal. So now, a lot of people wondering, what can you do next? So the radical, we're going to combine them because that's a different radicand. I mean, this one can multiply them, but you don't want to multiply them because that's also like different variable, different constant. So what we can do here next, we can rationalize the numerator. So using the technique that we've been talking about, you see the radical, so we can always multiply that by the conjugate. So multiply this top and the bottom by root a plus 2 plus root t plus 2. And down here on the bottom, root a plus 2 plus root t plus 2. Yeah, this one's a little bit tedious. So what we found, so is what, a plus 2 minus the quantity of t plus 2. And then it's all over. If we try to multiply this out, so this one, let's see. You don't want to multiply it out, so just leave that with that square root of t plus 2 times square root of a plus 2, because that eventually we can plug in that a here. And then times the quantity of the conjugate. And then don't forget that 1 over t minus a. That's a lot of element here, so we got to be very careful. So the 2 and the 2, we got cancel here. As you can see that we got a minus t. This one's t minus a. So a minus t, t minus a, the only difference is that the leading coefficient is -1. So basically we can just cross them out, a minus t, t minus a. So we just want to put in that -1 here. So we got -1 over, well, there's no more restrictions, so we can just plug in that a for t. So a plus 2 times square root of a plus 2, that's just what, a plus 2. And then this one, it's the same thing, root a plus 2 plus root a plus 2, which is what, 2 root a plus 2. And one thing that we notice, so we can multiply this together, so it's -1. Well, this one is just like adding, well, it's the same base, a plus 2 to the first power. And this one is what, 2 times a plus 2 to the power of 1/2. So it's the same base multiplying, so we can combine those exponent. So the 2, just put it right in front. And then quantity a plus 2 to the power, what's 1 plus 1/2? 1.5, which is what, 3/2. And this one here, that would be the final derivative of this function. Okay, so going back once again, so the last two problems, those are pretty straightforward. So each limit represents the derivative of some function of f at a. Stay such that f and a. So this one, well, this one using that the other form, so which is the h form for the derivative. So the h form for the derivative is showing that it's f of x plus h minus f of x over h. So compare and contrast. So h, that just shows the difference of the x1, x2 value. So what we found here, the function is actually considered cosine of something, cosine of x. Cosine of x, which is y equals, or f of x. Another thing that we notice, so f of x, or f of a, it's 1. So that means if f of a is 1, so that means we're converting it cosine of pi. Cosine of pi, well, it's not 1, it's -1, because positive, we can just put it in negative. So minus -1, so cosine of pi is actually -1. So the value of a, so I would say that is pi. Okay, so again, define that the derivative, well, the derivative is given, so you want to define that f and a. So for functions, we do have cosine of x. And then for a, which is pi. And this one, well, it's actually easier. So this one is quite obvious. So this one is showing the structure of limit x goes to a of f of x minus f of a over x minus a. So the value of a is actually given pretty obviously. So it's 5. And then for f of x, so that's just what? 2 to the power of x. And that's all you need to show. Again, if that's given directly with the a form for the derivative, it's pretty easy to define the value of a and f of x. If that's given as an h form, so you need to convert it. So got to be careful with the functions, the constant. You can always change the sign here. So that's it. So again, any questions, any comments that you have, so just put it up on the YouTube channel under the bar. And then I'll see you guys next time. So make sure that don't forget to subscribe to the channel. And also try to refer friends and people to my YouTube channel. Thank you for watching it. So I'll see you guys next time. Have a great one.